In this presentation, I'll introduce our work, Kasper, scanning for generalized transient execution gadgets in the Linux kernel. This is about 2.5 years of engineering effort between me and my co-author Jakob Koschel, and also our advisors Kaveh, Herbert, and Cristiano. So you may remember back in January 2018, there was a whole bunch of uproar about new vulnerabilities that surfaced, and of course this is Spectre and all the other sorts of variants, but Spectre, after a mispredicted branch, in particular Spectre v1, is the most lethal of all because it's the most difficult to mitigate. Because unlike the other vulnerabilities, Spectre v1, the way to mitigate it is you kind of have to employ like a whack-a-mole approach. You know, you have to find actual vulnerable code snippets, called gadgets, and mitigate these on a case-by-case basis. So it's quite difficult, you know, and at first mitigation was done just through manual effort, and developers thought like, okay, we got the low-hanging fruit, I hope everything's good, but in reality, like no one really knows. And so there's automatic gadget scanners to try to do this automatically, but still there's a bit of unknownness here. And so in this work, we present Kasper, a gadget scanner for the Linux kernel, and the previous talk motivated well why the kernel is a high-value target. And so we implemented this for the kernel. And the way we identify gadgets is by modeling the essential steps of a Spectre gadget. And we also model the different sorts of vulnerabilities and variants that are possible on a transient path. And as a result, we find over 1,300 gadgets. And we had kind of some heated discussions with the Linux kernel developers as to how to actually mitigate these gadgets. I'll get into that later. So first, of course, the question, what is a Spectre gadget? And so this is kind of the canonical example. There is our model here is a victim kernel and an unprivileged user process that is trying to attack the kernel, can issue syscalls and so on. And so this code snippet in the kernel, you know, it gets some data from user space, the get user API, all is well and good, that's expected. So it gets some untrusted attacker data, and then it hits some bounds check, and you know, if X is less than size, then it'll go into this branch here and access something from array 1. And so here in the array, I guess some of the characters didn't show up, but okay. So it accesses some kind of benign, boring data, and if the attacker data is greater than size, you know, like we would just expect that it does not take the branch and all is well and good. But the revelations of Spectre was that the microarchitecture actually executes this path kind of behind the scenes via speculative execution. And so what would happen is there's actually out of bounds access that happens under the hood. And so this could load secret data, and then the secret data would propagate, and if the secret data is then used as a pointer or something, this would affect the state of the CPU's data caches. This can leak to an attacker. So the follow-up question, you know, is how do existing gadget scanners work? And so the problem is that existing scanners, they're all entirely pattern-driven. So they'll look for specific patterns of the code snippet I just sent you, like suspicious copies from user space, or some out-of-bounds accesses, or some attacker-dependent accesses. And so the problem with these is that they don't actually model the Spectre gadget, they just model patterns of it, and we'll get into why later, you know, this results this has pretty poor results. And so another drawback of existing gadget scanners is that they all assume that they're limited in scope. And so they all assume the same primitives, attacker primitives, as the original Spectre v1 gadget that we're looking at. Namely, there's some direct attacker input, in this case from the get user API, there's an out-of-bounds secret access, and there's a cache-based covert channel. So this is kind of like the canonical example that was from January 2018. Every gadget scanner has targeted these features from this gadget. However, in reality, attackers do not care about patterns and conforming to what, you know, people think a gadget should look like. In particular, an attacker will exploit any instructions in the wake of any conditional branches that are controllable by any means, that load secrets in arbitrary ways and leak these secrets in arbitrary ways. So attackers do not care about these patterns. So if we go back to the previous slide here, this is, you know, as we said, this is kind of the Spectre v1 gadget. But there's a whole bunch of other transient execution vulnerabilities, such as LVI, Smother Spectre, Riddle, Fallout, Spectre Rewind. But wait, you know, there's more. There's just like tons of transient execution vulnerabilities that an attacker can use, you know. with all these sorts of primitives. And so an attacker has all these primitives at their disposal. If we're actually identifying gadgets, how can a gadget scanner even begin to model all of these different vulnerabilities? And so our approach that we introduced this idea of generalized gadgets. And so we modeled these generalized gadgets, and so we break Spectre gadgets down into the 3 essential steps that are needed for an attack. The first step is some injection of attacker data. And so in the case before, it was just like some user data from the get user API. There's some secret access, which before was some out of bounds read. And then there's the secret is leaked, in our case before, some cache interference. But there's all sorts of vulnerabilities that an attacker can use. So in particular, there's transient memory massaging, which as far as I know, we're the first work to actually introduce this as a concept. There's LVI, load value injection, which you can refer to the paper for more details on all these things, but I'll kind of stick to the standard Spectre v1 example in this talk. There's use after free reads that can load secrets, and there's MDS that can leak the secrets. There's port contentions, and there's all sorts of other covert channels and stuff that, these are just the most relevant ones to the kernel at least. And so, the next question is, all right, we have these primitives, but how do we actually identify these gadgets? And so we can walk through this example. So here we have the same gadget we saw before, except it's in a syscall handler. And so the first step that we do here, we do some dynamic analysis. So we actually run the kernel. In this case, we fuzz the syscall interface to model the coverage of a user space attacker. And so we run a bunch of syscalls with a bunch of inputs, and then we use dynamic taint analysis, so we add an attacker label to attacker controllable data. And again, we can plug in the different primitives here. So if we were doing LVI or attacker injected memory massaging, we'd also apply the attacker label here. And we can model these kind of generally. So I don't know if you can see, but the taint label applies there. The taint label propagates to the gadget at the bounds check here. And so at this point, we start what we call speculative emulation. And so normally, at runtime, if x is greater than size, it would just not take the branch, and all is good. But in our case, at runtime, we flip the branch and then model the speculative execution that was result from a branch misprediction. And so next, the taint continues to propagate. And then we have all these vulnerability detectors that we have inserted for memory accesses and branches and things like this. And so in this case, we have a memory error detector that would identify an unsafe access. So it's an out-of-bounds access. It's attacker controllable, so it declares this is an unsafe access. And so what we do is we would add a secret label to the output. So this is now secret data. And then this secret label would propagate to the next load, and then we have a cache interference detector that identifies this gadget because there is a dereference of a secret pointer. So that leaves a trace on the cache, and then the label would continue to propagate, and then at the very end, we reach the end of the speculation window, and then at runtime, we revert all the speculative operations. And so this is like all the memory writes. We keep track of all of them at runtime, and then we just undo all the memory operations. And then we go back to before the conditional branch, and then continue execution as normally. So speculative emulation is non-trivial to implement in the kernel. There's things like timer interrupts and inline assembly and DMA and MMIO and all these things, but you can refer to the paper for how we solve these challenges. So this is, so our implementation is for the Linux kernel. So we take the Linux kernel and we add some runtime libraries. We build the kernel with our LLVM passes to add things like taint analysis and speculative emulation. So we have a Kasper instrumented kernel that you can actually run, and then it reports gadgets at runtime. So we fuzz it reports gadgets, and then we get some kind of gadget statistics that a developer could use to mitigate. Okay. So first, we should evaluate this against previous approaches. So for this evaluation, we re-implemented previous approaches in the kernel, and then we ran Unix's ls command. And ls, runs a bunch of syscalls, and so we just looked at the gadgets that were reported when we ran ls. And so in particular, we evaluated SpecFuzz and SpecTaint, and then Kasper, but we limited Kasper to just the Spectre v1 primitives, not like all the primitives that we model. And so we can see here kind of the first takeaway is that SpecFuzz, it targets just the pattern, as we said before. It only targets speculative out-of-bounds accesses. And so as we can see, this leads to high false positives, high false negatives. SpecTaint, similarly, it only targets just like this pattern of identifying attacker-dependent accesses. It also has high false positives. And in our tool, we had some non-deterministic over-tainting that we observed, like on some runs. So this appears on some runs, but not others, and so because there is some non-determinism in the kernel. But overall, we have fewer higher quality gadgets. And so a developer trying to mitigate these gadgets, it's much easier to reason about 8 gadgets than almost 700. So let's get into the actual gadgets we discovered. So here we have a list of gadget types, and there's the left side is how the attacker data is injected. The right side is how the secret data leaks. So the first row here, we have user cache gadgets. So that's the original Spectre v1 gadget. Takes user data, leaks via the cache. And so we can take away here that the original Spectre v1 vulnerability remains largely unmitigated, despite all the hardening in the kernel. And so the next takeaway here is that we look at the LVI attacker data and then leaking via the cache. And we can see that LVI is indeed an issue from a conditional branch misprediction. And we're the first work to look at LVI within a conditional branch. So this is a new Spectre variant that we found, and we found instances of it. But we just kind of get this for free by plugging and playing different primitives, different vulnerabilities, and matching them up together. So we've essentially found a new Spectre variant this way. Next takeaway is that we have all these gadgets that use transient memory massaging to inject attacker data. And like I said before, as far as I know, we're the first to look at this as an attack vector. And so we can see that this is a legitimate attack vector. And of course, the high-level takeaway is that there are a ton of gadgets. And of course, you're probably all wondering, like, OK, it's great, but are any of these actually exploitable? And so we don't guarantee that they're all practically exploitable. We have some guarantees that we provide. But so as a case study, we can look at one of these gadgets that we found. It's in the kernel's list iterator. So anytime you have a list in the kernel and you iterate through the list, you use these macros, and there is a Spectre gadget. So it's pervasive throughout the kernel. And so let's go back to computer science 101. We have 2 pieces of data here, and we want to tie them together in a list. So we have some pointers, and it's a circular list, and there's kind of like this empty head. And so this is the kernel's linked list implementation. And so what you do if you iterate through the list on iteration 1, current element would be the first element. You load some data, you do something with that data within the loop, and then iteration 2, similarly, it goes to the next one. You do something with the data within the branch of the loop, and then the terminating iteration. It knows that it's the terminating iteration, so nothing really happens, but there's this kind of benign type confusion where the current element doesn't actually, it points to arbitrary out-of-bounds memory. And that's all well and good on the architectural path, but on the mispredicted path, we assume that an attacker can insert targeted data via memory massaging. And so actually, so this arbitrary data, it could be attacker controllable. And so, when on the mispredicted path, when some data is accessed, it's actually accessing an attacker controllable pointer. So some secret is loaded that the attacker can control what it points to. And then when the secret's loaded, it goes into the CPU's load buffer, and the attacker can leak this, exfiltrate this via MDS. So this list iterator gadget doesn't really conform to the normal bounds check bypass gadget pattern that we all know and love. So it's a totally different way of thinking about Spectre gadgets, but every time the kernel iterates through a list, this happens. And so finally, we implemented a proof of concept exploit of an instance of this gadget, but I think the more interesting story here is how to mitigate this. So to mitigate the gadget, the kernel has to first rewrite its list implementation, which, that's difficult, but it's it can be done. It's it'll probably be several patches, but it's all good. Next, the kernel needs to upgrade the version of C that it uses, and this is a non-trivial refactor, right? And we came to this conclusion after long heated discussions with the kernel developers, Linus Torvalds and Greg KH, and so there's this push. It might land as soon as the kernel 5.18, which comes out next month, to move the kernel from the 1989 version of C to the 2011 version of C. That makes it more amenable to this specific mitigation. But overall, there's more than 500 tree-wide patches that are required to implement a reasonable defense. So in conclusion, we looked at Spectre gadgets. We looked at how to identify Spectre gadgets. And we saw that previous approaches, which only identify certain patterns of the Spectre gadget, come up short. And so in response, we proposed and we implemented Kasper, a gadget scanner for the Linux kernel. And in Kasper, we model the essential steps of a Spectre gadget, and we model all sorts of transient software hardware vulnerabilities. And we find a bunch of gadgets, and there's ongoing discussions of how to mitigate these gadgets. And so with that, I'll take questions.